Hello, good morning, everyone. Welcome to class. People are trickling in and we will start. My three watches in the house, my cell phone, my hand watch, and my computer are all saying 9:10. So it must be 9:10, so we will begin. So we are in this week, week 10, if you can believe it. So we have come a long way, and we are going to be talking about a super important topic today, cross-validation. And this is not a completion of the things we have started about classification, but a very good point to look at it as a method. And we will spend almost all of the time we have discussing it. And I don't have any pictures today, but I have the two words. And it is a hyphenated word, which means both of them are going to play an important role in what we will be discussing. So before we get started with what we want to discuss, and I'm going to also remind you where we are in terms of topic coverage, I'm going to start with a warm-up question, just like we do. And people have started coming in. And my warm-up question for the day is going to be related to the words that are on the screen. And my question for you is this, and Swarnita, you will have the honor of writing today's warm-up question. I hope you're hearing me. So when you're ready, you will write. When you hear the word validation, what comes to mind first? That's the warm-up question for the day. And you don't necessarily have to think about data science, machine learning. You have a method you want to validate. That's great too. But just consider that word and tell me what comes to mind first. And you can, for now, ignore the cross part. Although, as I said, it is an important part of what we will be doing, okay? When you hear the word validation, what comes to mind? You're free to choose whatever it is that you feel like is coming to your mind first. All right. I have had a lot of fun yesterday meeting with people, groups. And so this is going to be a marathon set of meetings for me with kickoff meetings. I think most of you have started with your projects, so it's kicked off really, but we kick it harder, right? So we get started and we find out where we are. And if you haven't really got into it, it will also be a genuinely kickoff meeting. So I'm going to continue. And so after this one is over, my office hour usually that runs from 10:30 to 12 is extended by half an hour. So I've got 2 blocks. And so you've been very good at responding to things on the Google Doc we had. And so I've scheduled, and I think everybody is covered. So we'll continue doing this for the other 3 or 4 sessions I have today, and we'll have things set up, okay? So I'm looking forward to talking to those of you who are yet to meet today. Let me start by kind of see where we are. And I think this is a good thing to also know and to see. So we've done a lot of things. So I'm just looking back, and you've seen a picture similar to this one at some point, right? I really need us to kind of remember what covered and so on. It's easy to get lost, and sometimes you get too busy with too many other courses and so on. So we've got the topics that we have covered, 8 of them, right, on the left, and you've got a good list. And so the last set of things we have been doing is around classification. We saw logistic regression, we saw k-nearest neighbor, we saw linear discriminant analysis, we saw naive Bayes, and the very last thing we did on Monday, in fact, was to look at code for doing the classification methods we have covered, and particular logistic regression and linear discriminant analysis. We did them in one run. The k-nearest neighbor algorithm, I should tell you, when we discussed it, we spent good amount of time, really good amount of time, and saw topics that are related. But one of the slides at the very end, there is actually one slide that shows you how an R code would be used and what functions to call and so on. So we do have it. It's just that we didn't call it a lab, but there is one, just so you know and be familiar with it, right? So this is what we have covered. If you were to open up the syllabus now and see in the classification kind of subtopics I have, there is one thing left for us to do, at least for this course and the way we have time for, right? And that is about decision trees and random forest. And so I just wanted to continue. So everything we did, the done part is crimson, and what is left is gray. And so in the green part, I just continued with 8 because that's not done. And so decision trees and random forest will be the subject for next lecture, okay? We haven't forgotten that, and that is also something that is relevant both to regression and classification, and we'll see how that plays out. But there is a topic I called resampling methods, and cross-validation belongs there. Why resampling? When we start discussing it, I will show you. So that's our subject, and I don't have more than one lecture to devote to it. So have as much coffee sipping as you can, or whatever it is that you do to stay alert and follow me all along and take notes. But that's what we will do today, resampling methods. The topics that are the other ones are the upcoming ones, the things that are left to do. And so you can see a reminder, and they're all great topics to do, and make sure that you will be staying on top of things. What we have on the right bottom corner is all the assignments we have done, and assignment 5 is the last assignment we have in the term of assignments, and it is due on Friday. And so it deals with linear regression and classification. So this mapping between the assignments and what topics we have covered is actually a good one, and you will get a chance to take a look at them when you get to revise things. Okay, so this is where we are and what we are headed, and we're going to be, I need to remind you this one too, before we get really started. Okay, so we have the pieces of works we have to do: assignment, semester project, exam, class participation. Don't forget that class participation is important, and it carries 5%. And we've got an additional thing for 575 students about survey paper, which I talked about last time, and it carries worth and weights. We've got an awesome list of topics to choose from to propose a topic for what you will do for survey, but you may have even more interesting and nicer and better things that are fit to your interest that you could propose. Either way is fine, but that's due on Saturday, and so these are some reminders of the upcoming due dates. But so the October 30 ones, the October 31st one for 575 students. But after we have kicked off things and the project is started next week on November 4, I want everybody to tell me how things are going. That's what progress report would be. It's a couple pages, and tell me where you are, basically, the meetings we have had, the data set you have access. Here is exactly what we'll be doing. Here is what's left, and things like that. Okay, it's not going to be too much work, but I need to hear back because I don't want to wait until it is due in a way, right? And we all know that we have a late midterm, and that I have been saying all the time, the week of November 9. I am now leaning towards the Wednesday, November 11 as a date. And if we have really big reasons why we shouldn't have it, I will listen to you and we can change, but the week is fixed. We don't have other weeks to do it. So just wanted to have all the due dates and the things. I know some of you plan ahead things to have it in one slide. And so the final report is, of course, due on the very last, on the day we could have it. That's December 14. And for survey paper, for those of you who are 575 students, I wanted you to have a gap in between. So December 7th is the deadline for it. Okay. So this was just a reminder and to get us started. And I'm eager to get started with cross-validation. So I'm going to go there. And those of you who are still typing on what comes to mind when you hear the word validation, go ahead and do that. And so let's see. This topic, this discussion, like the series of topics we have had in the last 2 or 3 lectures, is going to be based on a chapter in the book that is called Introduction to Statistical Learning with Applications in R, and it is in chapter 5. So I just wanted to remind you that, and to remind you also that some of these slides that you will see there are inspired by how the authors have done based on lectures for that lecture. So if there is something that you want to go in more detail, that would be a place I would send you as a first reading. So I just wanted to start by saying that. Let me try to kind of motivate what we want to do. By the way, I didn't mention it, and you probably already know, the slides for this are posted on Blackboard. There's pictures in the beginning where we are and so on is not there, but the rest of it is there. So if you want to follow along, but it probably would be better if you follow me along here and take notes. You have told each other, and I am completely sold out on the idea that the best way to follow will be to take your own notes. And so I'll try to give you enough time, but try to take notes as we discuss. So I want to motivate why we would need something like this. And we are going to call this resampling method, which may sound a bit weird. Think about what you would do, and you probably have guessed the right way when I asked you what comes to mind when you hear the word validation. You want to make sure that something is correct. You get a validation. This is correct, or something that is pass the test. That's the kind of thing you have. And suppose now what we are dealing with is machine learning, data science, and we've got data and we've got, a method we have developed, and we wanted to know how well it is doing, and we have to validate it. And so if you think of the universe as a generator of things, then you would have liked to see how well you have done by taking another sample. You've got this thing that you work doing. You've got a population, and a sample would be a good way to call it. The data came from somewhere. Somebody, tracked logs or had a sensor, or it counted or sent out a survey, and it got given. And so you did develop a method, a model, and you worked on it, and you want to test it how well it did. So ideally, you would have to say, okay, go to the generator, to the universe again, and give me another sample, and then I'll use it here and show you how well it has done. Of course, we don't have that, right? The universe is not going to give us this data all the time, and so we test it here. And so instead, what we would do is use the very thing that we have and make sure that we are doing well by relying on the same thing. That's why it's called resampling. So we are using the same thing because we don't have access to more things. We use a clever way, a good way to make sure that we are resampling from the thing that we have access to. So we're going to look at cross-validation, which is one of the methods for doing this. And there is another one called bootstrap, which we'll mention maybe for 1 minute or 2 minutes in a follow-up lecture, but we don't spend too much time on it. These are the two major resampling methods. And so the idea is to refit a model of interest to samples formed from the training set in order to obtain additional information about the fitted model. So I wanted to know how this model is. I phrased it in terms of how well it is doing, but I wanted to talk about the model that I fit into the data that I have, but I wanted to kind of refit it to get additional information about it. That additional information could be an estimate, for example, on a test set prediction error. We're going to make this one clear in a second now. A test set prediction error will be what everybody wants to know, right? This is my method, and this is how it is doing on a test set. And to do that, we do this resampling method. Or we could also use it, especially the bootstrap method, to give some kind of statistical way to quantify how our parameter estimates are doing in terms of their standard deviation, for example. So if I want to talk about them, then I would need a method to resample. And bootstrap is a good example. So because now I have said, one of the purposes, probably the most common purpose, and the way you may be forced to do this, is to see how your method is doing on a test set. And for this reason, we have to distinguish between two types of errors. This should not be new to you. We may not have talked about this in this way, but we've been doing this in the labs we have had so far. And in fact, the last lab, both of the labs we have on the regression and on classification did do this, and I have shown you a few things there. So there is something called test error. This is how well your method is doing on and training error. The training error will be how well your method is doing on the data that it saw for training, and test error will be how well the method is doing on data that it is not used for training, but it is used for testing. So we have two things: test error and training error. And then I'm going to kind of make sure that you got me by saying it again. So the test error, if you want to have more with more words, is the average error that results from using your statistical learning method, your machine learning method, to predict the response on a new observation, one that was not used in the training method, which is the true test for you. Whereas the training error would be easily calculated by applying the statistical learning method to the observation used in the training. So if you remember, for example, when we were doing linear regression, there was a model we would fit, and even on the data point that were used for training, not a new one. When a new one comes and we want to predict, that would be our prediction, and there will be an error associated with it. But even on the ones that we saw for training, they were not fitting exactly on the line we drew. You remember that. There were plots we did and so on. So there would be an error. If I will take the actual value and what the predictor is saying, there will be a gap. In fact, that was how the whole thing came up, right? We were using linear square some of errors that to minimize that was the method used, and so there will be an error. That's what the training error would be. But the distinction is you are using it on the thing that the model has seen when it was being fit, whereas test error is on something that the model has not seen. The two are not the same. And the two could actually have a big difference in what they are trying to tell you. And that should not be very surprising. But the relationship between how they are is very interesting. And we have not spent time talking about this previously. And so just for a second now, not necessarily think about cross-validation, but think about a general truth. And so these curves are, you see two curves on this plot. And what this plot is showing you is a prediction error on the vertical axis and model complexity on the horizontal axis. What do I mean by model complexity? What I mean here is if we, for example, take linear regression as a problem and linear regression as our method. We remember we have seen both in your assignments, in the lab sessions, and in the discussions. There are different data sets we used, and linear regression could also be used to show when things are non-linear. And so we could use higher degree polynomials to estimate it because the linear fit was not really good. So it didn't follow the curve, how the data set is distributed. And so by increasing the degree of the estimation we are using, we could get a better estimate. And you have seen these things. And so when we have higher degree polynomials to estimate it, we will call that higher complexity. When linear was just good enough, then that would be low complexity. So think about models, and we could extend this type of thinking for almost all kinds of models. And so linear regression was the easiest one to think about. Classification methods are like that. So you can increase your complexity. You can increase your complexity means you lose some things. For example, you may not be able to interpret it in a good way, in an easy way. You may not go to a medical doctor and tell what your method is doing if it is very complex. Whereas something that is not trained in the kind of thing that you are told, you will be able to explain them when the model is of low complexity. And that is not only to talk to each other with people, but also for yourself, and you can interpret it. So what you see on the horizontal axis is an important topic overall when we assess models or talk about models. You can go from low to high. And when you go from low to high, and you are looking at what you're doing with your error, this is what the curves are tracing, and you are focusing on training error, then you would expect this to go continuously down. Why? Because after all, your model was trying exactly to do that. So here was something I was given. I'm going to stay with the the regression problem. And so the linear didn't fit well. And so I tried and did quadratic, and I did a higher degree polynomial. And if I did that with the goal of having to fit my model the best way possible with higher and higher complexity at the expense of losing a little bit of interpretability, of course it will go down. So your training error will continuously go down monotonically or in a continuous fashion, go down and down and down as your model complexity increases. That may not be the case when you apply it on a test set, on things that the model has not seen, but a new coming. And so if they would agree to a certain path, they would go together, they would go down the hill. And then at some point, the test error may start to actually go up, despite that your model complexity is increasing. And the reason for it is what everybody now knows, and you are included, you are overfitting. So you were trying to chase all the data points, and sometimes they could be noise, and just because they were there and you were trying to account for them, you built a model that is of higher complexity, and now when a real one comes, which is not necessarily going to be that wiggly, then you start to have higher errors, and so it could go up. And this is a very common thing. And so this curve is, in an abstract way, would almost always be true. Without knowing what the problem is and without knowing the exact data set, this would probably be true most of the time. So you could consider them as universal plots in a way. And people have come up with name. And this thing, when you have low complexity model, the prediction error will have high bias, which means you have not followed every single thing that you could follow. And so your model is biased, high bias. When you increase your model's complexity and trying to follow everything there, then you're trying to become faithful to what it is saying, and so you have low bias. What you have risked when you do high bias, low complexity model is that there is low variance, right? when there is high bias, there is low variance, because now you can imagine how it would behave when things change, right? So the variance there, it will be low. Whereas when you have increased your model, its complexity, and you have made it faithful to what you just saw, then it could have high variance, and that is the reason for why you would have overfitting and things that would inflate your error rate. Somewhere in between is the best thing, and this is usually the rule of thumb, right? So if things go up and down, so there will be a middle spot where things would be good, and that is what you would want to achieve. And this whole thing is called bias variance trade-off, this trade-off that you see. So find the model that gives you the sweet spot here, where it is of sufficiently high complexity and the error is low, but it is also not overfitting, and so the variance is not so high. Okay, I think it was worth spending time on this one and talking about it generally. And let me talk a little bit more about prediction error estimates more generally. So I have said this before, when I motivated it. If the universe was kind enough to give you new things all the time, so you wouldn't have to resample, so you would have tested it. You don't have that, and therefore we are going to be doing what we are doing, resample. But there is also other ways to correct, and this will be more mathematical. So the thing that we are addressing now, in the spirit of the nature of this course and empirical nature of it, we're going back to the data to get an answer and to get better methods and things like that. But that's not the only way of doing it. There is also mathematical ways in which you can adjust. And so you could now look at how to, kind of take into account what these variations are by modifying things. And that's what this list would be. I'm not going to spend too much time about them. I want you to be aware of them. Mathematical adjustments to training errors, so that what you would report on it would account for the potential of these variations. And you can quantify them. You can talk about them, and then you can, put them in a way that would give additional information about the model. But what we do now, as I said, empirically, will be we are going to play a game in some ways. We are going to say we are going to hold out a subset of the training set. The universe has given us only one thing, the data set that we have, and we have a distinction between training error and test error, and we wanted to do a method that has got a good variance bias trade-off, and we are going to now be mindful of how to do that, and therefore we will say we are going to hold out portion of the data we have, and we are going to be working on our training of this on the thing that we left out. So here is the thing that's hold out that will be used for testing, and we are going to train our model with the rest of it. This is the general idea we are going to be having that will take us. So we'll now do the thing without the hyphen. Okay, so the topic, the way I said when the first slide showed up, and I told you that there are two words in it, had cross validation. So for now, we're going to drop cross, and we're just talking about validation. And in fact, the technical name for it is validation set approach. This is what it is called. So what we would do now is, if we have to work with the data set that we have, maybe the first thing, or one of the things that would come to our mind would be, okay, let's go divide this data set into two. And we're going to break it up into two and randomly split it. And we use half of it for training, and we'll use the other half for testing. And that's not too bad sounding an idea, but that's one way to do it. The cross is not there. We just divided up the world into two. Here is where we will train. Here is where we will test. That's all we have done. And that approach is called validation. And that's what the first bullet says. So the model is fit on the training set, and the fitting model is used to predict the responses for the observations in the validation set. So the resulting error, the validation set error, provides now an estimate for the test error, because it was never used. Now we have not went back to the universe and asked for a new data set. Instead, we went on to the same data set we were given, split it into two, and then say, here is the data set we will train on, and here is the data set we will work on. And then we will report on the thing, because it was never used for testing, for training. So we'll report our test error on it. And so we could use, the mean square error, for example, when it is a regression problem, when the response is a quantitative one, and we could use a misclassification rate when it is a qualitative one. By the way, I should mention it now, and maybe I should mention it again. Everything that we will be discussing now in terms of having to validate would apply to either of these classes. So for a good portion of it, I would make it will be easier to think about these errors, mean square errors, and so it will be more quantitative, but don't think this is just for regression. But it also applies to classification. The only thing we need to change is what we are using to measure error. In one case, it will be number, right? This is the error, and in other case, it will be a little bit of whether we have got it right or wrong, misclassification rate, but both of them are just fine. Okay, so the validation process goes like this. We have the data set, we split it into two, in this case, blue and orange. We train on the blue and test on the red. And the split is done randomly. That is all there is about validation, the validation set approach. Let's see how this works. And we're going to go to our automobile data set. We have seen this before. And we may remember, you have also played around, I think in one of your assignments, that linear model was not, when the power one with the linear model was not a good fit, but higher order. And I think we saw the quadratic one was actually a better one. And so this, what you see here is that same data set, an actual data set. And we're going to investigate how the degree of the polynomial that is used for it would influence the mean squared error you would get. This is a test error. And so the plot on the on the left is the mean squared error versus the degree polynomial, 1, 2, and so it goes all the way up. And in this particular case, this plot is errors, right? So the errors are recorded and they are plotted. And so we have used 392 observations, and it's split into two, exactly equal, 196 in each case. And what you see here is the error rate. And so the actual number about what the error is probably not too important. But what is important on the left curve is linear is bad, but the degree 2, the quadratic one was 1. It significantly reduced it. But then when we start increasing the degree, okay, from 2 to 3 to 4, it didn't help much. In fact, there was a case when it actually went a little bit up and then it came down. So lesson number 1, on this particular test data set, a linear model was a poor fit, quadratic was better, it minimized, and going up higher didn't help. That's the story, and finished. And it's probably not too surprising for that particular data set to find quadratic to be a good one. So increasing the complexity of the model beyond 2 did not help. What you see on the right is what happens. This is a test error that you use with this type of modeling. We still are doing higher, linear and higher and things like that. So the curves are showing. But what we're doing now is all kinds of ways to split it in half. So if I've got a data set, 392, and I'm splitting it into 196, 196, I could do it one way. I could do another way. I could put, certain things on the left and certain things on the right, and I could change this in a number of different ways. And so there are 10 of them here. So 10 different ways, or however many these plots are. Now you're seeing the variation in error when you do this split. A few things to observe. First, there's a lot of variation. So depending on what you're doing for your splitting, the error could go up and down very much, right? So there is a big difference between what the yellowish curve shows at the very bottom and the brownish curve shows at the top in terms of these actual errors. Why did that happen? Well, it depended because on how I'm doing in my splitting. But their patterns were very similar. So this stayed true to how the method is working, the quadratic one being the best one and things like that. That stayed true, but the errors themselves varied a lot. This is a big lesson to learn. This is a problem with this validation approach when you just split things into two. But that's not the only problem. If you were following me, and if you probably have seen this before or thought about this before, maybe you wouldn't be surprised. But if you were hearing it for the first time, and I just told you what I just told you, you would say, you're wasting a lot of things. You were given a data set, and it's not true that I always get a lot of data for whatever I want to do. No, you're just taking half of it. That's really unfair. You're taking a whole lot of things that you could make use of to make the model behave in a good way and come up with a model that would be a good predictor, but you just threw half of it out the window. That's not good. And we paid the price for it because we saw how we split made a big difference in how these errors are coming. And so that's a disadvantage. And the other thing is, okay, you can forgive me for taking half of it out and wasting, but you could also say, what about what you're getting on this other half that you tested on? It's going to be really an overestimate because you could have done better by having the test error estimate itself could have been more informative if it was not for this major kind of strategy that I have taken now. So I did take a whole lot of things out, and it is an overestimate. Here comes the solution. Here comes the cross part for the topic. And now we're going to be smarter. And so we are going to kind of play around, and we're going to reuse things. So we are going to this validation in a fashion that goes, I know some of you are fans of skiing. I never was a good skier, but I have pretended as if I would go. So cross-country skiing, think about it. So you go this way, go this way, go. So that's what we will do. And we'll do this in K-fold. And so we'll use this K. And I've told you computer science is fond of this letter K, wherever it is, K nearest neighborhood. K was the parameter of choice. And so we'll use another K, but this one tends to be written in capital K, for whatever reason. So we are going to avoid the ills of validation by looking at cross validation. And it's a very widely used approach for estimating test error. And it will fix it because it would give a more realistic error, and it would give us a way to account for the weakness we just saw. So the idea is to divide up your data into K folds, K blocks, equal sized, and we're going to leave out part K, one of them, use the other, the remaining ones, to train and record the errors on the ones that are with this one left out, and then swap the roles. And so bring another one of the other codes, and then we repeat this for all of them. We have a complete description here, and I have a picture that probably is friendlier to understand. Let me first see how much I'm doing on time. Okay, we're fine. And if I kind of speed up, understand why I'm doing that. I'll tell you first kind of an empirical value people have found and is good. 5 and 10. You may wonder why 5 and 10, but they're good. And they have been used very often. If it's not very surprising if you open up any paper that's published and then add the method, when they come to the place where they would say how they validated their method, and they say they used cross-validation, good for them, then they would say 10-fold cross-validation. That's very, 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 very common because it's a good way to get things done. And so it depends on the data set that you have. And so between 5 and 10, if you really have smaller things, probably 5 would be better, but 10 is a good general guidance. So in this one, it is illustrated with 5. So you will use one of these for validation, and you're going to train on these other 4. They should be equal sized. The first one looks a little bigger in this cartoon, just because I wanted to fit the validation with more text, but the details are here. So what you do is find, and I'm going to talk about regression problems. So we've got the mean square error. When the case, the one that you hold out, is left out, you go around and find what the error is, and you sum them up. So the role of the box that is used for validation is going to change. So the first time you use box 1, the next time you use box 2, the third time is 3, 4, and 5, in the case where K was 5, and you add up the mean square errors that you leave when the one that is left out is left, right? And so you aggregate this, and now you would have the CV. This is not a CV like your resume. This is cross-validation, and you add up the K that you had, and then you have a number to go out, to go report about this, how this method is doing. Notice what I am using looks like an average. So this is a summation, but it is an average, weighted average. And it's because your data set may not very nicely kind of divide up into 5. And so there could be something that you would round up and down. That's one thing. But you may also have a reason to make just one or two off than the other one. So to just account for that one, you've got this NK divided by K, which is the weight that you are associating with each one of these blocks. So this is a way to get the number, okay? There is a special case. There is a special case where you would say, instead of 5 blocks or 10 blocks and so on, what if I did one item in each one of these blocks? So I'm just hold out just one of my sample, my cases, and then taste on n-1 of the other ones, and then repeat this thing. So that's called leave one out cross-validation, and it has got an abbreviation like this. I'm going to tell you something very quickly about it, and then we will move on. So first, it may sound like you are going to the extreme case you could go. And so the splitting into half, the validation one was bad, you wasted, and so on. And so you're dividing things up into folds, and so use one at a time to validate and then add up these things. And if you went all the way to saying each one of these folds now has got just one, then you would worry, and maybe my next slide would say you're doing too many computations. So you're refitting too many times, because I mean, how many, if you've got 100,000, then you're going to do this thing 100,000 times. And so that sounds like very expensive to compute. And there is other things that's not good about this. I'll mention it in the next slide. But this slide has got something that would tell you that's a savior. It says you don't have to, when you have leave out one cross validation and you've just one item and then you have to refit on that, you don't have to actually refit this all the time, endlessly, n-1 time, because there is a very nice mathematical result that you can show that would tell you this number that you're after right from the get-go. And this one has got a connection with what I told you about leverage when we were talking about linear regression. And so this applies for regression problems only. And so you could actually find a number that would tell you what the impact of that particular one that you are leaving out, I in this case, is going to be. And therefore, you don't have to do this n-1 times and get these values. You actually have it for free. You have it for free by doing some good math, and R and some other packages would give you this. This is called the Hat matrix. And so this one kind of tells you the influence one item has in a big data set on the overall error that would come. And by using that one, which is what this displayed equation here tells you, you can have the close validation error for when you have n items, and you can get it this way. So we did solve the computation part, which sounded so crazy. If you were to do n-1 times to refit a model, you would probably end up finishing the rest of the semester just running a code for having to get this number. You don't have to do that because you can save it, but it has got other problems. The other problems are good enough for us not to rely on it, and therefore use k equals to 5 or k equals to 10. And it is because it checks the data too much. Because now all that we wanted was to have a good way to get the variance, bias trade-off and have a good handle for knowing about our test error. And now because we just picked one and then use the rest of the data to train and then come back to this one, there isn't really so much of a difference between what each of these models are. It's just they differ in one. So it's not useful. We're just using the same data set all the time. It's how it is. So because of that, it doesn't serve a good purpose. It doesn't shake up the data so very well. And so we instead choose k equals to 5 or k equals to 10. So come back to the auto data set and look at the thing that I said validation is a bad idea because there were so many curves that were going up and down. Look at what k-fold cross validation did on this. The same curves, now we have k-fold cross validation, which means we're going to divide this thing up into k, and k, by the way, here is 10, but I've got very many ways to divide up things into 10 boxes, right? I could put one thing here, another thing, and that would be one k-fold. And then I could also have another way to get same k equals to 10, but this time I have packed them slightly differently. And so I could have very many different. See how robust this thing is to these variations. And so you can see almost the curves just lying on top of each other. The thing on the left is the leave out one cross validation, the thing that did not shake up the data very well and things like that. So I wanted to see on the right is the 10-fold one. So kudos for 10-fold because it's doing what this other one is doing, but it's with less computation and with less variability about how these other things are working. This is a curve or a discussion that talks about what you would do on a simulated data. And the only way to make good use of what these curves are showing is to tell you where it is located in the book and ask you to read about the curves, because I don't want to spend too much time about talking about each of these curves. And so it's figure 5.6 in the book. And so the blue curve here shows you the mean square error. And the black and red curves, if you can see the distinction between black and red, are the estimated mean square errors for two models using k-fold. And then the k here, I think, is a 10. And so what you see is mean square error, and what the flexibility of the model is changing. And the point of it is really to show you that the k-fold is doing a good job. And it also is showing you, for this particular one, it is a simulated data set. A simulated data, that's why you have the blue one. I should make that point very, very clear to you. If somebody tells you you have a true error curve for something, that should be kind of a paradox, right? How would I know a true error? In this case, because it is a simulated data, I know what it should look like, so I can talk about the actual true error. And so that's the point this slide is wanting to show you. So let me invite you to read that portion and read it if you have more interest in learning about it. What do I want to talk about this? I don't think there is so much I want to tell you about this one. Right. So the empirical result for choosing k equals to 5 or k equals to 10 can be supported analytically. And this is something that you should probably appreciate, right? So I told you k equals to 5 and k equals to 10 would shake up the data better, and they are empirically found to be good, and people use them. This is one way to justify. The other way to justify is to actually see if there is some analysis that you can do to make sure that there is at least a range where something like this would be valuable, good choices. And this is the point this slide is trying to make, the first point that I'm trying to make, because each time you are taking a plot, a block of these divisions that you have and holding it out for validation, you're testing on k minus 1 of these other ones. And so its relative proportion to k has a bearing on what the test error is saying. And that one goes in our favor when k is equal to 5 or k equals to 10. This is the math equation I want to display when things are not regression problems. I told you, and the only thing that would change is what we are using to measure what error is. When it was a regression problem, we used mean square error. That's what we have seen in very many of the slides. But we don't have mean square error when we have classification problem, but we have misclassification rate. And that's what this ERRK now shows you. And this is the where you have made mistakes. This is what the label was, but this is what you predicted. You predicted a dog when it was a cat, so you misclassified. And so that difference is what the error would be. Everything else is exactly the same compared to what we discussed so far. What you see in bullet 3 talks about the estimated standard error. And you could, much like what you would do when you have a plot, and if you do carefully, you would say how variation is, and you would show here is the plot, and here is what the bar would be around it and its variation. You could do something similar for the test error that you got, and that's what this equation here is showing you. I have got 5 minutes for something. I want you to be very alert, and I know you're alert and you're listening to me, but be very alert and listen to me even more. And this is because there is, unfortunately, times when people use cross-validation the wrong way. And so I want to tell you when it is done the wrong way. And the wrong way comes because of a real need, a real situation people have. Half of the projects that I know you'll be doing, and for those of you who I haven't talked, one common situation you may have is this. You've got data set, and this data set has got lots of potential predictors, lots of things that could potentially be predictors, and you don't know which ones are good. And so one of the things you would do is screen. You could have different ways to find out which ones are good predictors and so on, but it's a common problem. So you want to reduce from a potentially a large number of predictors, the ones that are good, the ones that would be help your model do a good job in prediction. So you do select something like that. And so because of that, there is a potential for doing cross-validation the wrong way. That's where the setting is. So consider now, and to make this one a little more complete, you are starting with 5,000. This is exaggerated, of course. You've got 5,000, or genomics probably has got, or maybe some of the stats students in the class might actually be dealing with something like this in genetics and things like that. It's not it's not that exaggerated. It could well be true. Start with something like 5,000 predictors, and you've got only 50 samples. That was the number of people you could get their bloods taken from, or whatever it is, right? It's really, scarce. You don't just go there and get samples. You've got only 50 of them, and you've got 5,000 predictors, and you saw how their correlation is and so on, and you find out that there are 100 predictors having the largest correlation with the class labels. This is a classification problem. That's what you found out in step 1. So we applied then a classifier, for example, logistic regression, on those 100 predictors. Why? Because they were the ones that we found out after doing the correlations with the class labels, the best ones. Now we're going to say, we wanted to know how our method, in this case, logistic regression, is doing on this classifier. Can we just then, because now we did the step 1 screening, basically, to find out what are good predictors, can I just go ahead and do cross-validation in step 2 and call it a day? Forget about step 1. No, you shouldn't do that. This is because what the whole point of what cross-validation was doing was to say, I'm going to hold out a data set, train on what is here, and then test it on this one, and record the error and find out how it's doing and report it. When I have 5,000 samples left out after I studied them, left out 4,900 of them and just picked 100. And now I'm going to do the cross-validation on the second step only. I'm cheating. My training had seen all of these 5,000, left out things that were not useful and so on. But when I come to report on how well it is doing, I am now testing it on something that what my training step had access to. And that will not be right. So you could be getting a very good result after the fact that this thing has been used. What you should do instead, to talk about the entire method, is to apply it in both steps, in both step 1 and step 2. Then you could talk about cross-validation, and what you're talking about the method is now the right way. You may have, and you will have, error rate that you would report when you applied it on both higher. That's for sure, but that's the right one. And that's how you should be doing it. And people have studied this and see how many times it's done the wrong way. The way just I told you in publications that, referee, peer-reviewed type of publications especially in the area of genomics. Genomics is picked here just because it had this tendency to have predictors that are too many, very many, and you have to select good ones among them. So you shouldn't do that and apply it to both steps. That's applying it to just step 2 is wrong, and applying it to both step 1 and 2 is right. Let me pictorially show you this, and then we will stop. And we are just about time to stop. This is the wrong way. When you have the predictors, all of them are displayed like this, and you've got the selected ones on the left, and you've got the outcomes. That's the response. And you did now cross-validation folds on without having to worry about how the outcome was, and you did it this way. That was the wrong way. And the right way instead is to divide up your K folds before you apply the cross-validation ahead of time. And so your output, the response variables, is also divided. You could go ahead and do on the K-1 you have, whatever it is that you want to do, right? Now you have divided this up, and the holdout says is also equally done that way. And so now you can report results on this one. This one agrees with how we were doing things when we were selecting, when we were not cherry picking, which predictors to use. When we were not doing that, we did this. Why should we change our mind now when we are doing it on a select set? And so it's a little bit subtle, and probably sometimes people, when they do it wrong, they don't do it intentionally. But here is, I think, an excellent way to pictorially see what is happening. And if you wanted more the wordy way to say this, here you have the 2 steps, apply cross-validation to both, not to just the second one, would be a quick word to say. That's the last slide I have, and this is just about a good time to stop. Let me see if you have any questions for me. Everything was clear? Okay, I'll take it as a yes. All right, for those of you who will be seeing 10:30 today, or in the block from 10:30 to 11:30, welcome. And those of you who are coming after that, one thing I want to tell you is if there is somebody I'm talking to while you come, just join, no problem. And you will not be using the office hours Zoom link. This is my Zoom personal room, and it's set up for everybody. So make sure that you go there. Don't go to the wrong place and miss me. But you come to the place where it has got my name and it looks like a phone number. It actually is a phone number, my office phone number. That's where you will come. Okay, I will stop here and I will see some of you today and the rest of you on Friday.